be looking at science paper 1. Specifically, we are going to look at radioactivity. So this is an important topic that you need to know in science paper 1. So it usually comes on question B9, and the saying figure B9.1 shows the deflections produced when radioactive radiations passes through an electric field. So radiation or radioactive elements or radiations, they are affected by one electric field. They are also affected by magnetic field. So it just depends on the nature of a certain radioactive sample that is passing through the current or electric field as well as the magnetic field. So here we have the negative charge here on this pole here. Then we also have a positive charge on this pole. So you have to understand the nature of the radiations from this source here. So let me start with alpha. So for alpha, it is positively charged. So you are going to judge according to the nature of these radioactive elements or radiations. Then we also have beta. So for beta, it is negatively charged. So it has a nature to that of a high-speed electron. Then for alpha, it has a nature to that of helium. Okay, so it has 4 here and then 2. Then for an electron, it is this one. Okay, then let's come to gamma. So for gamma, it is neutral. So it has a 0 charge. It doesn't have a charge. This one, it has high frequency. It has high or highest frequency compared to these. So it has a 0 charge. Now, according to the charges that we have here, and these are the charges of the electric field we have been given, and these are the nature of these radiations we have here. So what are we going to do? We have to come up with a principle to say that for a positive charge and a positive charge, these, they don't work. They won't attract. Unless you have a positive charge, you also have a negative charge. This one is going to work. Again, you can't have a negative charge and a negative charge. This one won't work as well. So this is what we are going to use. So according to radiation A, it is bending toward the negative charge. So guess which radiation? Is it beta, is it alpha, or gamma? So if you guess A to be alpha, then you are correct. The result is very simple. The positive charge will always follow the negative charge. So A is alpha. Then B. For the radiation B, it is gamma. It is not affected by either the electric field or the magnetic field. This is the only radiation which is not affected by these fields. So B is gamma. Then for C, definitely it is going to be beta, because here we have a positive charge and beta is negative. So negative is going to follow the positive charge. Alright, so identify the radiations represented by the letters A, B, and C. So A is alpha radiation. Then for B, it is going to be gamma radiation. Then C, it is going to be beta radiation. Question B. Which of the radiations A, B, or C would be most suitable to prolong the shelf life of tomatoes? So let me just explain here the uses of these. So let's start with alpha. So alpha is mostly used in smoke detectors. Smoke detectors. So in hospitals, in banks, or even in houses. So when there is fire and smoke is produced, we have the devices which has the alpha particles, and these they are able to detect smoke. So once smoke has been detected, you're going to find that maybe water will start coming out from those devices in order to whip out fire. Then another thing, we have beta. This beta is mostly used in monitoring the concrete, if there are cracks there, or it is used in the monitoring of the pipes. If there is leakage, you can use beta. Then for gamma, it is used for preservation of foods. So in order to preserve tomato, gamma is going to be used. That is one thing that you have to know. So gamma radiation. So you can just say B instead of saying gamma. Let me just say B, because it is saying which of the radiation, A, B, or C. So just need to write B. No need of you saying gamma. Then we are here. Question C. We have cobalt 60 is a beta emitter with a half-life of 5 years. So we have been given half-life here to be 5 years. Okay. So since it is a beta, the question is saying what is the nature of beta emission? So the nature of beta emission is high speed electron. So we can say high speed electron, or you can just say the nature of an electron. So beta, it has a nature of an electron. For gamma, it has a nature to that of a neutron. Then for alpha, it has a nature to that of helium. Roman number 2. What are the proton number? What are the proton number and the nucleon number of the mass, or let me say of the nucleus, after beta emission from cobalt 60 nucleus? So let me just write something here. For beta emission, if we have X here, it has a mass number. It has also the proton number or the electron number. If it emits by beta, let's say it produces Y. Okay, what is going to happen is that the mass number is going to be added by 0, or it is just going to remain constant. Then when it comes to the proton number or the electron number, it is going to be added by 1, so that is B plus 1. Then you write the nature of an electron or the nature of beta emission, which is 0. Then we write beta, then negative 1. So this is how you're supposed to write. So now we have cobalt 60. So the nucleon number is this one here, the combination of the proton number as well as the electron number, I can say. So what we are going to do here, the nucleon number is also known as the mass number, so it is just going to remain the same. So it is 60. What about the proton number? The proton number is going to be added by 1, as you can see. So we have 27, so it's going to be 28. Then we are done. The last one is saying calculate the time required for the activity of a freshly prepared sample of cobalt 60 to 4 to 1/3, let me say 1/32 of its initial value. So for us to answer this one, you have to know the equation. The original mass divided by the initial. So in this case, it is 1/2, then to the power n. So n is representing the number of half-lives. Then there is also another formula. Number of half-lives is equal to the time taken divided by the half-life. So here what we are looking for T, which is the total number or the time required. So time required is going to be equal to number of half-lives multiplied by the half-life. So for us to calculate the time required, we have to calculate n. Okay, once we calculate n, then it is going to be very easy for us now to find the time required. So let's use this formula here. One thing that you have to know here is that original mass divided by the initial mass, we have 1 over 3 or 1 over 32. Sorry for that. So we have 1 over 32, and this is going to be equal to, we have 1 over 2 then to the power n. So we know to say that we can convert this 32 into 2 to the power 5, isn't it? So 2 to the power 5 is same as 32. So what am I going to do? I can say we have 1 over 2 to the power 5, and this is going to be equal to 1 over 2 to the power n. Then from there, I know to say that I can take this 5, then put it outside, because it is not going to affect, it is not going to have any effect on 1. So I'm going to write 1 over 2 to the power 5, because 1 to the power 5 is same as 1. Then 1 over 2 to the power n, so that these, they can cancel each other. Then my value of n is going to be 5. So we can now calculate the time taken here. So the time taken is going to be equal to the number of half-lives, which is 5, multiplied by the half-life. So the half-life we have been given in the question, which is 5. Then when I multiply, I'm going to get 25. Remember, the units are years, so it is 25 years. So this is how you're supposed to answer this one. Thank you very much for watching.